Information moved beneath streets and between floors through sealed tubes driven by compressed air. The system was hidden inside walls, under pavements, and along basement corridors. Messages written on paper were placed into metal carriers shaped like cylinders. The carriers were inserted into openings connected to the tube network. Air pressure pushed them forward at speeds a walking courier could not match. The path was fixed. The destination was determined before the carrier entered the system. No one handling the message saw the route it traveled. The tube carried it in darkness from one station to another. Buildings that required fast internal communication installed these networks to avoid delays caused by human movement. The system did not depend on visibility. It depended on air pressure, sealed paths, and the certainty that a carrier inserted at one point would arrive at another. Speed was mechanical. Routing was predetermined. The message moved because the tube allowed nothing else.
Tube networks followed the structure of the buildings or districts they served. Vertical tubes ran between floors. Horizontal tubes connected departments or separate structures. Junction points allowed carriers to be switched from one line to another. The tubes themselves were made of brass or steel. Diameter was standardized to fit the carriers. Bends in the system were gradual to prevent carriers from jamming. Stations were placed at points where messages needed to be sent or received. Each station had an insertion slot and a receiving bin. Air pressure was maintained by pumps located in mechanical rooms. Vacuum pressure could also be used to pull carriers through the line instead of pushing them. Some systems used both. The layout of the tubes was mapped, but the map was not visible to those sending messages. Routing instructions were written on the carrier or entered at the dispatch point. The system moved the carrier according to those instructions without further input.
The carrier was a hollow cylinder with a cap that screwed or latched into place. It was made of metal or hard rubber. The interior was sized to hold folded paper, small documents, or currency. The exterior was smooth to reduce friction inside the tube. Felt or leather rings encircled the carrier to create a seal against the tube wall. This seal allowed air pressure to act on the carrier. Without it, air would pass around the carrier and propulsion would fail. Loading required the message to be inserted, the cap secured, and the carrier placed into the dispatch slot. Once inside, a lever or button activated the air system. The carrier accelerated instantly. It traveled in complete darkness. There was no window. There was no light inside the tube. The carrier moved until it reached a station where air pressure dropped or reversed. It then fell into a receiving bin. The bin was checked at intervals. Messages were removed and delivered by hand from that point. Workers maintained flow and cleared failures. Carriers sometimes jammed at bends or junctions. When this happened, air pressure built behind the blockage. The system had to be depressurized before the obstruction could be reached. Access panels were built into the tube network at intervals for this purpose. Workers opened the panel, removed the jam carrier, and closed the system again. Misrouted carriers were another issue. If a junction switch was set incorrectly, the carrier traveled to the wrong station. It had to be retrieved and resent. Some systems included indicator lights or mechanical counters that tracked carrier movement. These allowed workers to confirm that a carrier had passed a checkpoint. If it did not, the route was inspected. Workers also replaced worn seals on carriers and checked tube interiors for cracks or corrosion. Air leaks reduced pressure and slowed transmission. The system required constant attention to function reliably. Silence meant operation. Noise meant failure. Institutions that required rapid internal communication depended on pneumatic systems. Banks used them to move transaction records between tellers and back offices. Hospitals sent laboratory results, medication orders, and patient information between departments. Stock exchanges transmitted bid and offer slips during trading hours. Newspaper offices moved copy between writers, editors, and typesetters. Government buildings used tubes to communicate between offices without messengers walking through corridors. Department stores connected sales floors to accounting and inventory rooms. The system reduced the time required to move information from minutes to seconds. It also reduced the number of people needed to carry messages. A single tube could replace multiple couriers. Dependence on the system grew as organizations designed workflows around its speed. Messages that once waited for a runner now moved continuously. The tube became infrastructure. Its operation was assumed. Failure disrupted work in ways that were immediate and visible. Expansion was limited by cost and space. Adding new stations required drilling through walls and installing additional tubing. Rerouting an existing line was difficult once the system was built into a structure. Maintenance became more complex as networks grew. Tube sections wore out and had to be replaced. Pumps required regular service. Seals degraded and had to be renewed. Noise was a secondary problem. Air rushing through tubes produced a hissing sound. Carriers striking the walls of receiving bins created impacts that could be heard in adjacent rooms. Some buildings insulated the tubes to reduce sound transmission. Reliability declined as systems aged. Carriers moved more slowly. Jams became more frequent. Institutional dependence made failures disruptive, but the cost of replacement or major repair often exceeded the budget available. Systems were patched rather than rebuilt. Performance decreased gradually. The infrastructure remained, but its effectiveness diminished over time. Electronic communication replaced physical transmission. Messages that once moved through tubes began moving through wires. Telephone systems allowed voice communication without carriers. Teletype machines transmitted text without pneumatic pressure. Internal computer networks later eliminated the need for physical message transport entirely. Institutions that had relied on tube systems found electronic alternatives faster and less expensive to maintain. Pneumatic networks were shut down, pumps were turned off, carriers were removed or left in bins. The tubes themselves remained inside walls and beneath floors. Removing them required demolition that was rarely justified. They were abandoned in place. Buildings continued to function. Communication continued. The infrastructure that had supported message flow for decades became inactive. The system did not collapse, it simply stopped being used. The tubes remained where they had been installed, sealed and silent, carrying nothing. Some tube networks were repurposed. Sections were used for cable routing in buildings undergoing electrical upgrades. Others were left completely untouched. Maintenance workers occasionally discovered them during renovations. The tubes were still intact. The stations were still mounted to walls. Carriers were sometimes found inside, messages still folded within them. These messages had been in transit when the system was shut down. They never reached their destination. The pneumatic infrastructure was durable. Brass and steel did not decay quickly. The tubes could have continued functioning if the pumps had been reactivated and the seals replaced, but there was no reason to restore them. Electronic systems had taken over the role completely. The pneumatic network had become a relic, embedded in structures that were still in use. It was not removed because removal required effort. It was not restored because restoration required need. The tubes remained as installed, functional in design, but inactive in practice. Buildings constructed during the pneumatic era often retained architectural features designed around tube systems. Small openings in walls marked former dispatch and receiving stations. Mechanical rooms contained pumps that were no longer connected to anything. Blueprints included tube layouts that were no longer relevant, but remained part of the building's documentation. New occupants of these buildings rarely knew the tubes existed. They were hidden behind plaster, beneath flooring, and inside ceiling spaces. Only during major renovations were they rediscovered. Contractors drilling through walls encountered metal tubes that had not been documented in modern plans. The discovery usually led to confusion, then identification, then a decision to work around them rather than remove them. The tubes were not hazardous, they were simply obsolete. Their continued presence was incidental. The buildings had moved on, the communication methods had changed. The infrastructure remained because there was no compelling reason to extract it. Pneumatic tube systems carried information until they did not. The transition was not dramatic. There was no final message ceremony. Institutions simply stopped using them. The carriers stopped moving. The air pressures stopped cycling. The system became part of the building's hidden structure, like old wiring or decommissioned heating ducts. Some tubes are still there. They run through walls and banks that no longer operate as banks. They connect floors in hospitals that have been rebuilt around them. They thread beneath streets that have been repaved multiple times. The network still exists in physical form. It no longer serves its original function. No one sends messages through them. No one waits at a receiving station. The tubes remain sealed, empty, and silent. They are infrastructure that was not removed because removal was unnecessary. The system persists not because it is used, but because it was built to last. The tubes are still there, carrying nothing.